There are two types of equilibria. One is homogeneous equilibria and the heterogeneous equilibria. So I will just give you one simple example of the homogeneous equilibria and I will define it. Here, homogeneous equilibrium. Homogeneous Homogeneous equilibrium is when reactant and the product at equilibrium are in same phase. That is like reactant, the product will be in the same phase like gaseous phase or liquid or solid. So let's take one example. We can take this way. A nitrogen, this is also a gas. Hydrogen, this is also a gas. In equilibrium with, let's say, the product form is NH3. 2 moles. Now, equilibrium defined for this type of equilibrium is called as homogeneous, where the reactant is in gaseous phase and also the product are in the gaseous phase. Now, heterogeneous equilibrium is when the reactant and the products are in the different phases. For example, right, heterogeneous equilibrium. The reactant and the product are in the different phases. For example, a calcium carbonate, CaCO3, is in equilibrium with calcium oxide. This is solid, and the carbon dioxide gas. Like if you see, this is calcium carbonate which is solid. The product form is one is gas and the other is solid. So here the reactants and the products are in the different phases. Here this type of equilibrium is called as a heterogeneous equilibrium. So we have done with the homogeneous and the heterogeneous equilibria. Let us understand the more details of the homogeneous equilibrium and let us understand how to write the equilibrium constant for the heterogeneous equilibrium. The thing is the active mass of the solid is unity. One I will write for the heterogeneous equilibrium. Heterogeneous equilibrium. First condition, like if this is the condition, like if there is a solid and the gases and the liquid, then if there is a solid, I will say that active mass means concentration of solid is unity. Means for example, you take this equilibrium calcium carbonate getting decomposed and there is a equilibrium between a calcium oxide, this is also solid, this is also solid, and the carbon dioxide gas is formed, right? While writing equilibrium constant, you will be writing this way: equilibrium constant will be is equal to concentration of the calcium oxide, that is product, and calcium concentration of the carbon dioxide divided by calcium carbonate. Right here, if you see the calcium carbonate and calcium oxide, they are in the solid phase. So whenever it is in the solid phase, we consider the solid phase concentration to be unity, means 1. So what will be Kc will be is equal to, Kc will be equal to alone a concentration of the carbon dioxide over here. So this is as good as writing 1 into concentration of carbon dioxide divided by 1. Therefore, Kc will be is equal to 1. Sorry, not 1. Kc will be equal to concentration of carbon dioxide. Next is second is active mass of liquid. Active mass means concentration of liquid in equilibrium with gas is unity. Means if there is a, let's take a simple example, H2O liquid is in equilibrium with H2O gas evaporation process. So here what will be Kc? Kc will be is equal to concentration of H2O in gas phase divided by concentration of H2O in the liquid phase product upon reacted. So here this will be unity, this will be is equal to Kc will be is equal to concentration of gas upon 1. Therefore equilibrium constant will be written alone in a concentration of the gas. Yes. Third is for equilibria, aqueous medium. For equilibria in aqueous medium concentration of water liquid is unity. Let's take this example. Aqueous CH3COO minus, this is aqueous, dissolve in water liquid, and what you get is acetic acid CH3COOH, aqueous plus OH minus aqueous. Right? This is what we are getting. Now over here for equilibrium in aqueous medium, concentration of H2O is unity. Means if you are going to write the equilibrium, like such type of situations occurs when, like if there is very large amount of the water, see solvent and the solute makes solution. So solvent is in very large amount, okay, let's say 10 liter, a very small amount of the solute you are adding. So the concentration of the solvent remains unchanged, right? So concentration of the solvent doesn't change in the process. So here water is in very large amount, very small amount of the acetic acid is being added, and that is being dissociated over here, that is being reacted with it, and we are getting this equilibrium over here. So here equilibrium constant, directly if we are going to write, then it will be a concentration of the OH minus, right, upon concentrate into concentration of CH3COOH. Like these both are in the aqueous medium. Here this is also in aqueous medium, right? Aqueous means it is dissolved in water, it is there in the water, and this itself is water, right? The concentration of this is going to remain unchanged, okay? So concentration of this will be like there won't be any change in the concentration of the solvent. So this I am writing H2O, but since it is in the aqueous medium, liquid is considered to be unity. So H2O, concentration of H2O is considered to be 1. So over here Kc will be alone due to only these things. So OH minus CH3COOH minus. So this is the thing about the different types of heterogeneous equilibria. So let us discuss about the units of equilibrium constant. Okay, here topic is units of equilibrium constant. We'll take different examples, and we will try to learn units of the equilibrium constant. Let's take this. Let's take a first reaction. I will take, we'll mark first reaction, and let's take this N2. This is gas, and this is O2, which is gas. Gives you N2O2 gas. Right. This is what we are getting. Sorry, this is 2 moles of NO. 2 moles of NO. Here, equilibrium constant will be a concentration, since all are gaseous reactor, here a concentration of NO raised to 2 divided by concentration of O2 raised to 1, concentration of N2 raised to 1. So concentration of NO will be, like if I represent it in moles per liter, then this will be the concentration. Here also it is raised to 2, here it is moles per liter, and here it is moles per liter. Right. So what will happen? This 2 and this is going to cancel. This doesn't have unit. No unit. No unit. Right. This won't be case for all the reaction. This won't be a case for all the reactions. So if I consider another reaction like PCl5, this is a gas getting decomposed to PCl3, this is also a gas, and giving you Cl2 gas. But if you write the equilibrium constant, here Kc will be is equal to concentration of Cl2 into concentration of PCl3 divided by concentration of PCl5. No doubt you can also express, since this is in a gaseous reactant, you can also express these things in a atmosphere in terms of the partial pressures also, right? But let's take this in the concentration. So Kc will be is equal to, over here this will be moles per liter, right? This will be in moles per liter. So here this is moles per liter, right? These 2 units is going to get cancelled. So over here I am getting unit to be moles per liter. So depends what is the value of delta n. Okay, delta n is 0, then there won't be, if there is a delta n is 0, then there won't be any units for the equilibrium constant. Next, learn reaction this way. So here, let's take this reaction. Third reaction I am writing. Then it is CrO4 2 minus. Let's take this aqueous. Then Pb2 plus. This is also aqueous. This is in equilibrium with PbCrO4. This is solid. Right? We can consider this case. This is a reaction. So this is in aqueous, and this is in the solid, heterogeneous equilibrium. So equilibrium constant, what we are writing units, right? For that we will write a equilibrium constant. It will be concentration of PbCrO4. This is in solid, and here this is concentration of CrO2 minus, and this is concentration of Pb2 plus. So what will be this Kc? This will be, since this is unity, this is just 1, and here a concentration, I will not consider any concentration of this, so I will write this is moles per liter, and this is also moles per liter. So what will be the units for this will be mole, units of Kc will be this. One more reaction, let's take one more reaction. Fourth example I'll take this way. Let's take an example where there are solids. Okay, let's take a solid. Let's take a Fe and H2O. This is gas and this is solid in equilibrium with Fe2O4. plus gas. Let's take this is solid. Equation is balanced. 2Fe. Here I'll put 3 and let's take this 3 moles and no, not over here. Okay, let's take this reaction and just focus on the stoichiometric coefficient. Just give me a second. Just check the stoichiometric coefficient. Okay, here is a mistake. Fe3O4. Now I guess the reaction is balanced. 8 and oxygen 4 oxygen 4. Yeah. So this is the reaction. If you want to write the equilibrium constant for this, then we are going to write it in this manner. Concentration of Fe3O4, right? This is solid. Concentration of H2 raised to power 4. This is concentration of H2O raised to power 4, and there is concentration of Fe raised to 3. So here, in this case, this is in gaseous phase, this is in solid, and this Fe is in solid. So I will write 1 into, here I will write the unit, that is moles per liter raised to 4, and here also I will write moles per liter raised to 4. Fe is in solid, so this is I am writing 1 raised to 3. 1 raised to 3 could be written directly to be is equal to 1. So again this and this is going to get cancelled, and there is no units for this. This is how we write the units of the equilibrium constant.